Hey there, focused learners, and welcome to this explainer. Today, we've got a thrilling, microscopic detective story lined up just for you. If you're a grade 10 physical sciences student looking to absolutely ace your electrostatics exam, well, you are exactly in the right place. Get ready because we're about to crack the case of the missing electrons.
So let me ask you something. Have you ever pulled a fluffy winter jersey over your head and felt that tiny, surprising zap? Or maybe you've heard that little crackle in the dark? Well, consider that your inciting incident, because that tiny, unexpected spark, that's the literal crime scene for today's physics mystery.
Okay, let's dive right into this. Straight out of your Sayavula textbook, electrostatics is officially defined as the study of electric charge which is at rest or static. Basically, that means the charges aren't flowing in a continuous current like they do in a plugged-in circuit. Instead, they're just hanging out, building up on surfaces, and waiting for the absolute perfect moment to jump.
To make sure we cover your annual teaching plan and exam guidelines perfectly, here is our detective checklist. 1. What is electrostatics? 2. The story of charges. 3. Contact and conservation. 4. Charge quantization rules. And 5. Calculating the electron jump.
All right, Section 1. What is electrostatics? The hook.
The technical term you'll see straight from your exam guidelines is triboelectric charging. This is a specific type of contact electrification. Basically, it's just charging an object by contact or rubbing. When you rub two different materials together, like say your hair and that fluffy jersey, the friction causes absolute chaos down in the microscopic world, forcibly separating charges between the two materials.
Moving on to Section 2, the story of charges. Meet the suspects.
Let's meet our two main characters. Over on the left, we've got the protons. They're heavy, positively charged, and tightly bound deep inside the nucleus of the atom. Total immovable homebodies. On the right, the electrons. These guys are tiny, negatively charged, highly mobile, wandering escape artists. And here is your absolute golden exam rule. During triboelectric charging, only the electrons move. The protons stay exactly where they are. No exceptions. So, when we talk about the charge of an object, we're really just talking about a fundamental imbalance of these tiny escape artists. If an object has equal protons and electrons, it's neutral, no net charge at all. If it's positively charged, that means it is electron deficient, it lost some of its electrons. And if it's negatively charged, it has an excess of electrons. It gained those wandering escape artists.
Which brings us to Section 3, Contact and Conservation, the incident.
Now, what's really interesting about this is how the DBE exam guidelines explicitly lay it out. The universe absolutely loves total balance. When two conducting objects touch, they don't just stubbornly hold on to their own charges. Instead, they interact and they share.
And this introduces a massive, absolutely crucial concept, the principle of conservation of charge. You really need to memorize this exact phrasing for your exam. The net charge of an isolated system remains constant during any physical process. Think of it kind of like two friends deciding to fairly split a lunch bill. The total amount of money doesn't magically change, it just gets distributed equally between them.
And here is the mathematical formula for that fair split. Q new equals Q1 plus Q2, all divided by 2. You simply add the initial charges together to find the total net charge and then divide by 2 to figure out exactly what each object gets. Just remember the crucial caveat from your guidelines. This super simple equation is perfectly true for identically sized conductors on insulated stands.
Okay, Section 4, Charge Quantization Rules, the interrogation.
So according to the exam guidelines, charges don't just ooze around in random continuous blobs. Nope. The universe has incredibly strict, non-negotiable rules for counting them. They move in highly specific, quantized packets.
Here is your next big definition to enthusiastically memorize. The principle of charge quantization. All charges in the universe consist of an integer multiple of the charge on one electron. Let me just repeat that key part, an integer multiple. That means you can have 1 electron jump, or 5, or 1,000,000, but there is absolutely no way you can have half an electron jump. It's whole numbers only. And what is the actual literal charge on just one of those single electrons? Well, it's this magic number right here, 1.6 times 10 to the power of negative 19 coulombs. This is your QE, the fundamental, non-negotiable ticket price for a single electron. Every single total charge in the universe is just a multiple of this ridiculously tiny number.
Let's put all the clues together. Section 5. Calculating the electron jump, the climax.
To reliably crack this case on your exam, just use this foolproof 3-step scaffolding method. Step 1. Find the final charge after they touch, the Q new. Step 2. Find the difference, the delta Q, which is just Q new minus Q old. Step 3. Count the electrons using the formula N equals delta Q divided by QE. And honestly, this brilliantly illustrates just how beautifully logical the exam math actually is when you break it down into steps.
So the crucial point is this, and you've got to remember it. To find the missing electrons, always find delta Q first. A really common mistake students make is plugging the final charge straight into the N equation. But remember, we are investigating the change at the crime scene. We need to know how much charge actually moved from one sphere to the other, so we absolutely must use the difference.
All right, let's wrap up our microscopic investigation with these essential, bite-sized takeaways that you can easily store in your memory for test day. Rule 1. Only electrons move. Rule 2. Touching identical objects share their charge equally. Rule 3. Find the change, that delta Q, first. And Rule 4. Divide that change by the magic number, 1.6 times 10 to the negative 19 coulombs, to find your number of electrons.
And just like that, the mystery is totally solved. Next time you pull on a fluffy jersey and feel that static spark, will you be able to calculate exactly how many of those tiny escape artists just jumped? I'm pretty sure you will. You are now totally equipped with the formulas, the guidelines, and the understanding to completely ace this section of your physical sciences exam. Keep practicing those equations, stay curious, and keep learning.